Hello and welcome to the YouTube channel D Creations Resources. We are looking at different topics from mathematics, especially linear algebra, and today we are going to talk about a topic called row canonical form or row reduced form of a matrix. If you recall, we had earlier seen the row echelon form of a matrix and we had seen it in details. There were around 4 episodes on it. So first we understood what it meant, what properties did it have, and in fact if you look here, the first 3 properties, they will seem familiar to you because they are same for row echelon form as well as row reduced form. But in row reduced form, we go one step ahead. So there are 2 more additional characteristics as well. We had seen the uses of row echelon form, and one of them of course was solving linear systems of equations. We had solved a system of equations using that format and also done a multiple choice question, etc. So if you wish to revise it, you can always go back and see those episodes. Now this particular form, row canonical form, also has important applications such as solving of linear systems of equations, finding the basis of a vector space, and finding inverse of a matrix. Now it is very important that whatever we learn, the question that we ask is, why are we learning it? What is the motivation? What is the use? And here you can see that the reason why we are learning this row canonical form or row reduced form of a matrix is because it has so many applications. Now I hope you are familiar with the terms such as basis or inverse of a matrix because we have done several episodes on these concepts. So if you have forgotten them, please go back and revisit those episodes. Coming back to row canonical form or row reduced form of a matrix. Well, I can give you a typical example of this. So instead of listing down the properties one by one, we will keep on looking at the corresponding example so that the point becomes much more clear. So a unit matrix is always in a row canonical form or row reduced form of a matrix. That's why we said that this is the simplest form in which the matrix could be converted to. So here you can see that. Let's go at the properties one by one. First 3 properties, as I said, are similar to row echelon form, such as all the 0 rows, if present, are at the bottom of the matrix. Now here there are no 0 rows, so there's no question of it. Had there been there in another example, they should have been at the bottom. The first non-zero entry in each row, called a leading entry, another name for this is pivot, is to the right of the leading entry in the row above it. So in the first row anyway, there is no problem. Look at second row. What is the leading entry? This is the leading entry, 1. Is it to the right of the entry in row 1? Yes, it is. Similarly, go to row 3. What is the leading entry? This particular position. And is it to the right of the entries in row 1 as well as row 2? Yes, it is. So this is satisfied. Next, all elements below a leading entry are 0. Now this was there for the row echelon form. In fact, it gets modified when we go to row canonical form, and if you see the last characteristic here, it tells you the modification. All entries above and below a leading entry are 0. So here if you look at this row 2, leading entry 1, you can see that above and below, they are all zeros. So in fact you can in other words say that this has to be the only non-zero entry in the column, the leading entry. And the leading entry also has to be 1. Look at characteristic number 4. So it can't be some random non-zero number. So again, this is an additional characteristic for the row reduced form, and a unit matrix would be a perfect example. As you can see, it has all the characteristics. There is no 0 row, so there's no question of that characteristic, but otherwise you can see that leading entry in every row is 1. All other entries in the column containing the leading entry are 0, and the leading entry in the next row is to the right of the one in the previous row. So all the conditions are satisfied. Now let us go ahead and try to convert a matrix to its row canonical form. So let's go to this matrix. Now we are going to make use of row operations, of course, and the aim, as you know, is basically making all the other entries containing the leading entry as all the other entries in the column containing the leading entry need to be 0. So first you can see here 2 and minus 1 are here. So obviously if you want to make it 0, you can add row 1 to row 3 because minus 1 plus 1 is 0. Also you can subtract twice of row 1 from row 2 because 2 minus 2 is 0. So this is what you will get. But now also pay attention to the fact that you don't have to just convert these entries. When you say row, you have to convert all the entries in that row. Now row 1 is going to remain unchanged because no modification is being made to row 1. In fact, row 1 is being used to make modifications to other rows such as row 2 and row 3. So row 2, all the entries minus 2 into the entry corresponding entry from row 1. So minus 1 minus 2 is minus 3. 1 minus of minus 2, that means 1 plus 2 is 3. So row 2 is complete. The R3 plus R1. So minus 1 plus 1 is 0. 2 plus 1 is 3. 2 minus 1 is 1. So we get this form. Now we concentrate on the second column. Here there are a couple of things that you need to look at. First of all, you need to have the center element as 1. Also the other elements need to be 0. So here let us add row 2 to row 3. So basically 3 minus 3 this will give you 0. Also later if you divide this by minus 3, the element is going to become minus 3 divided by minus 3, which is 1. Then there are some more entries. Of course there is this 1 which you will need to make as 0, and in the third column these two entries also you will have to make them to be equal to 0. So simply if you add R3 to R2 as well as to R1, life is going to be simpler. So you can see that this is 1, 1 minus 1. When you add R3, R3 just consists of this 1. So as you know, this 1 arose because we divided row 3 by 4. So when you just add it, this becomes 0, and to R2 if you add it again, this element becomes 0. Now what is the last step remaining? The only entry which is forbidding this particular matrix to be a row canonical form is this 1. You need to make it to 0. So simply you can subtract row 2 from row 1 and this is what you get. So finally you have reached the row canonical form 1 0 0 0 1 0 0 0 1. It is a unit matrix. Now let's quickly look at its application. See, we have done all these operations. We are going to make use of the same operations but with something additional. See this system of equations. X plus y minus z is equal to minus 2. 2x minus y plus z is equal to 5. And minus x plus 2y plus 2z is equal to 1. If you just make a matrix out of the coefficients of these equations. So 1, 1 minus 1, 2 minus 1, 1, minus 1, 2, 2. Look at what matrix we had earlier. See, 1, 1 minus 1, 2 minus 1, 1, minus 1, 2, 2. Minus 1, 2, 2. So basically this was the same matrix over which we had performed row operations and got to the unit matrix. So now here the coefficient matrix is the same. Into the matrix that we are multiplying it with is the matrix containing a column where the entries are x, y, z, and on the right hand side you are going to get a matrix containing all the entries here on the right hand side, minus 2, 5, 1. So if you perform the set of operations that we did here, the end result was this matrix got converted to the unit matrix. So that is what you can see here. It has got converted to the unit matrix. Now how about doing the same operations on this particular column vector containing minus 2, 5, 1 as the entries? If you do it, finally you are going to get the result as 1, minus 1, 2. So in fact this is going to be unit matrix into the column vector xyz is equal to 1, minus 1, 2. So that itself gives you the solution that x is 1, y is minus 1, z is equal to 2. So the answer here for this system of equations is this 1, minus 1, 2, the column vector that we obtained when we performed the same set of row operations that we had performed on the coefficient matrix here and led to a row canonical form, basically the unit matrix. So this is a quick example of application of row canonical form or reduced form where we are solving a system of equations. Now in the next episode we are again going to solve a system of equations and there it will become clearer. So I would suggest that after seeing this immediately see the next episode so that the idea that how we are able to solve a system of equations using row canonical form or reduced form of a matrix will become much more clear to you. Thank you.